So if I run this, and now I need to decide the shape of a matrix. So I'm going to say shape is equals to, let's say the matrix is of size 1000, 1000. And then I can set the time steps or the number of times I want the matrix to be multiplied. So I'm going to say step is equals to 200. And then I can create my matrix. So I'm going to say mat is equals to tf dot random dot normal. And inside there, I'm going to pass the shape of my matrix. So I'm going to say shape is equals to shape. And if I try to print matrix now, it will return me a matrix of size 1000 into 1000, and now I can pass this to my function. So what I'm going to do is I'm going to say measure, and inside there I'm going to pass the matrix that is mat, comma the time steps that I want it to work for. So steps, yeah. And if I try to print it, it will return me the time it took to actually perform these three operations. And now I can also, by the way, this is using the GPU, but if I wanted to actually use CPU instead of GPU, what I can do is I can say with tf.device. And inside there, I can pass the name of the physical device that I want to use. For example, I want to use CPU 0. And if I pass it over here, and if I run this code within this with statement, it will work using the CPU version of TensorFlow. So as you can see, it took us 5 seconds, but if I use the GPU version, it took us 1 second to actually perform all those, actually less than 1 second to perform all those operations. So other than that, we can also create a tensor using tf.constant. So if I wanted to create any kind of tensor, for example, if I have a NumPy array, suppose this one, and I want to convert it into a tensor, what I can do is I can say a is equals to tf dot constant. And inside there, I can pass my NumPy array. And now if I try to print a, it will return me a tensor that has these values inside it. Okay, so as we saw that when we are using the CPU version, it is quite slow, but when using the GPU version, it is quite fast. But the main reason that it is fast is that GPU is better when it is actually processing your data. But CPU is slower at that time because CPU actually has to get all that information from the memory, but GPU has a larger memory, so it can actually store all the information inside the GPU instead of going to the secondary memory or ROM. So, but overall, the training time for both the CPU version and the GPU version is same. But since CPU is slower in processing the data, so GPU version is much faster as compared to CPU version. Okay, so next we have TensorFlow graphs. So what TensorFlow does is it actually creates a graph before performing any kind of operation. For example, if we have this this equation over here, what TensorFlow will do is it will actually create a graph for it before actually performing these operations. For example, we have, if we say that a is equals to 15 and b is equals to 5, what TensorFlow will first do is it will first create this graph. For example, a into b, that is this one, and then the addition part, which is this one, and then it will divide the results, that is this part. So so once the graph is created, it will actually pass your values through to the the TensorFlow graph, and it will give you the results. And this is the main reason that why we are able to run our TensorFlow models on different platforms instead of them being a programming language dependent. They are independent because they are graphs. So you can run graphs on any platform. But if you were working in any kind of programming language, then you would need the compiler for that programming language. So TensorFlow avoids that part by actually creating the graphs for your calculations. So by the way, this is a tensor, and this is what we call a rank 0 tensor. So tensors have ranks. For example, a scalar is a rank 0 tensor, and a vector would be a rank 1 tensor, and a matrix is a rank 2 tensor, and a rank 3 tensor would be a stack of matrix, and we can increase our ranks as much as we want. So what that means is that your data's dimensionality can be as many dimensions as you want. For example, you can have a 10-dimensional data or 20 or 30 and so on. Okay, so what are the benefits of using these graphs in TensorFlow? So the first reason is that when we import any saved model from TensorFlow, it is actually saved in form of these graphs. That allows us to run that graph on any platform, and so that way we are not bound by the language that we built that application in, or that model in. The second reason is the compile time. When we are using graphs, it actually uses something called a constant folding. What that means is that you are actually deciding which operation to perform first and which operation to perform last at the compile time, instead of actually deciding it on the runtime. So like when we are actually saving our model, or we are actually compiling our models, we create those graphs, and then we can directly transfer those graphs to any platform, and it would run without any problems by just passing the inputs through it. So the another advantage of using graphs is that it allows us to perform these operations separately. Like for example, I can perform this multiplication operation in a single thread, and I can perform this addition in a separate thread. That allows me to actually perform these operations at the same times. That saves my time of doing it separately. Like for example, if I was using Python, then it would first evaluate this part, and then it would evaluate this part. But if I'm using graphs, these both parts are evaluated at the same time. So another important use of graphs is that it allows us to skip some part of our calculation. For example, if we have redundant operations on the same tensors, we can skip those parts if we are using graphs. This part is quite similar to how we perform operations in dynamic programming. So, so this also saves us a lot of time and computation power. So in short, using graphs allows the TensorFlow to run faster and in parallels, which makes it more efficient on various multiple devices. So, so basically graphs are what makes TensorFlow so versatile and allow us to run them on various different platforms. Okay, so next is what are the differences between the TensorFlow version 1.0 and 2.0. So the main difference between the version 1.0 and 2.0 is that in version 2.0, we have a new concept called eager execution. So in TensorFlow 1.0, what we had to do is we had to create graphs for performing even the smallest of operations. For example, if I wanted to add two numbers, I would first need to create a graph. So creating a graph actually takes a lot of time, and it is actually wasting our resources when we do not actually need to create a graph for just adding two numbers. So this new concept called eager execution, what it does is it skips the part where we create a graph and directly performs those operations like you would in a normal programming language like Python. So in the version 2.0, a new type of tensor was introduced called the eager tensor. So for example, over here we have this tensor called A. Now, if I try to look at the type of A, it would return me the type that is eager tensor. So what that means is that when you try to perform any operation on this, like if you are only performing a simple operation without starting a session, then it would be performed directly using the rules from Python programming language, or the language that you are actually working in. So in TensorFlow, we have this concept called a session. So session is basically what allows you to perform operations on your graphs. So if you want to like pass your tensor through a graph, you actually need to start a operation, or sorry, you actually need to start a session. So what eager tensor does is it actually does not need to be inside a session to actually like, if you want to perform any operation on a eager tensor, you do not actually need to start that session. Okay, so other than the type, you can also look at the type of data that your tensor has. For example, I can say a dot d type, and it will return me the type of data that is inside it. So it should be int32. And you can also look at the size of your tensor. For example, if I want to look at the size, I can say the shape, and that will return me the shape of my tensor. Okay. So the next biggest change in TensorFlow 2.0 was that most of the libraries from TensorFlow 1.0 were removed. Like, for example, in TensorFlow 1.0, we had to actually start a session for performing any kind of calculation. But since the release of TensorFlow 2.0, you do not actually need to start a session. That is taken care of by TensorFlow backend. So TensorFlow will automatically decide whether a session needs to be started for a certain graph or not. So the next one is that the Keras API. For example, in TensorFlow 1.0, the use of Keras API was quite limited, but since the release of TensorFlow 2.0, you can do almost all of the calculation that you would do in TensorFlow directly from the Keras API. And the biggest change in TensorFlow 2.0 is the release or the introduction of a new library called datasets. So what this library allows you to do is it actually allows you to cache your inputs. So instead of importing all the inputs directly from the secondary memory, what you can do is you can divide those inputs into small chunks of data, and then store them inside a cache instead of so you can like directly access it from the cache instead of going to the ROM and accessing that memory. Okay, so next what we have is TensorFlow or TensorFlow variables. So what variables allow you to do in TensorFlow is that it actually allows you to save your data outside your sessions. For example, all the operations in TensorFlow are performed inside sessions, and once that session ends, all the data from your tensors is it is lost, because mainly because it was built upon Python, built using Python. So this is how it works. So once you stop your session, all the data inside that session will be lost. But to avoid that, we can actually use something called a TF variable. So what it allows you to do is it actually stores that data so that you can transfer it to another session. Other than storing your data, variables also allows you to set whether the data should be, or the variable should be trainable or not. For example, when you are training a new model, you can have a variable called weights, and you can decide whether you want to train your weights for a certain variable or not. For example, your variables can be layers or a neuron or anything you want. So it also has the option of whether you want to actually train your variable or not. So the way that you declare a variable in TensorFlow is that you say first you need to actually have a tensor. So I'm going to create a rank 4 tensor. I'm going to say rank 4 is equals to tf dot zeros. By the way, all the operations that we have in NumPy are automatically imported into TensorFlow. So if you are wondering what different operations are available to you in TensorFlow, so if you have done NumPy before, you can use all the operations from NumPy directly in TensorFlow. So I'm going to now create a rank 4 tensor. So I'm going to say 3, 4, 5, and 6. And now I can actually store this rank 4 tensor inside a variable. So I'm going to say variable 1. Inside there, I can pass the tensor that I want to store. For example, I want to store the rank 4 tensor. And now if I try to print variable 1, it will have my rank 4 tensor, but but the data type or the type of this variable is going to be tf dot variable